Null. Hydrothermal alteration zones. Zones of hydrothermally altered rocks are associated with all types of VMS deposits. These zones are petrologically distinct and they either cross-cut or are semi-conformable with the volcanic stratigraphy. The alteration is produced by reaction of a hot, metal-rich fluid with the volcanic or volcanically derived wall rocks. Hydrothermal alteration and zones patterns. The alteration zones around and below VMS deposits are defined by the alteration minerals present, their chemistry, and their distribution. These vary considerably, but of importance is that they can be classified according to number one, the VMS deposit type they are associated with, number two, the volatile fragmentation depth. In other words, the style of volcanism and the associated depth of water are important controls on the alteration minerals and their distribution. The volatile fragmentation depth (VFD) is defined as the water depth at which volatiles will exhale from a magma rapidly enough to tear the magma apart, pyroclastic eruption, or rapidly enough to allow external water to trigger explosive disruption, hydromagmatic. The VFD differs for the different kinds of VMS deposits. VFD and VMS, Noranda and Cypress types. These kinds of VMS deposits form below the VFD, and thus there is little or no products of explosive volcanism in the stratigraphy. That is, they form in relatively deep water. The stratigraphy is thus dominated by lava flows and domes. Thus, porosity and permeability of the rocks is low, leading to alteration zones that are narrow, straight, and well confined. These deposit types are found in dominantly mafic volcanic stratigraphy, and this creates a distinct mineralogical and chemical alteration signatures. Matabi-type. These VMS deposits are hosted by rocks that formed above the VFD, and thus the stratigraphy is dominated by both explosively formed fragmental rocks and clast-bearing sedimentary rocks formed by erosion and mass wasting of the explosive volcanic products, that is, shallow water and lots of explosive volcanism. Thus, permeability and porosity are high, and this creates alteration zones that are much more widespread, irregular, and poorly defined. These deposit types occur in dominantly felsic volcanic stratigraphy, leading to distinctive alteration assemblages. Crocokit type. These kind of VMS deposits for both above and below the VFD, that is, in deep and shallow water. Overall, the volcanic stratigraphy is composed largely of felsic lavas and domes, and thus porosity and permeability are relatively low. Thus, alteration zones are narrow, confined, and straight. VMS and hydrothermal alteration. As mentioned above, VMS deposits have extensive zones of hydrothermally altered volcanic and sedimentary rocks, derived from erosion of the volcanic material. These zones vary in the kinds of minerals present, their geometric shape, and their size. These variables are a direct reflection of the environment of formation of the volcanic rocks as well as the source and nature of the hydrothermal fluids. Overall, alteration is a great exploration tool. Noranda-type bimodal mafic. The alteration associated with Noranda-type deposits can be subdivided into pipe-like and semi-conformable. Pipe-like alteration. Well-defined and confined pipe-shaped alteration zone, which is mineralogically and chemically zoned. This alteration type cross-cuts stratigraphy, varies from 100 to 400 meter wide and 300 to 1500 meter deep. It narrows with depth and at the top is slightly wider than the VMS deposit. The alteration is controlled by syn volcanic fault structures, pipe-like alteration. Within the alteration pipe, there is an inner iron chloride quartz plus minus clay zone that gives way outwards to a middle zone of magnesium, chloride quartz, sericite, clay minerals, which grades into an outer zone of sericite quartz clays, kaolinite, montmorillonite. Pods of talc may be associated with the middle zone. The stringer ore occurs in the inner zone and a pyrite can be found throughout all the alteration zones. Semi-conformable alteration. This alteration type occurs as regionally extensive areas of altered rock up to tens of kilometers long and 1 to 3 kilometers deep. It may extend down to the subvolcanic intrusion and up to the Paleocene floor. Semi-conformable alteration may be difficult to recognize because, number one, it is mineralogically similar to zeolite, greenschist, and possibly amphibolite grade metamorphic assemblages. It may be recognizable or distinguished based on the abundance of the minerals present and their distribution. That is, a greenschist grade basalt should not contain 70% actinolite or epidote and have this concentrated only in permeable horizons such as amygdaloidal flow topes and hyaloclastites. Number two, the alteration is patchy. It comes and goes and is most intense along the most permeable rocks and horizons. Mineral assemblages include number one, zeolite alteration, rare in older rocks, common on modern seafloor. Number two, sepalitization, similar to a greenschist grade mineral assemblage of chlorite, albite, actinolite, tremolite, quartz, epidote. Number three, silicification, quartz albite most prominent in mafic rocks. Number four, epidote, epidite, quartz, actinolite. Number fifth, carbonate and kerrite, ferruginous dolomite. Silicification. This is a common alteration type in the semi-conformable zone and represents an increase in the SiO2 content of the rocks. It is most pronounced along permeable rock horizons like fractures, faults, pillow selvages, etc. It forms by either a addition of SiO2 to the rock, that is, the hydrothermal fluid was saturated in silica, b. leaching of calcium, sodium, potassium, magnesium out of the volcanic rocks, leaving excess Si and Al, aluminum. Sepalitization. This commonly occurs below the silicified zone and it consists of epidote, tremolite, actinolite, and albite. This alteration is patchy. Epidote quartz may form rocks called epidocytes. This is also similar to regional greenschist metamorphism, composed of epidote and quartz, all green rocks. The intensity of this alteration assemblage increases adjacent to syn-volcanic faults and syn-volcanic intrusions. This alteration type is believed to define higher temperature reaction zones in mafic volcanic rocks. It represents an increase in SiO2, CaO, and Na2O, and a decrease of potassium and some iron, copper, and zinc. Crocockit type by model Felsic. Alteration assemblages associated with these deposit types are the mirror image of the Noranda cypress type with The difference due to the dominance of felsic or mafic rocks. More potassium, silicon, sodium, less iron and magnesium. Thus, there is a well-defined and a constrained alteration pipe with an inner zone composed of sericite quartz, clays iron, chloride, which grades out into a zone of iron magnesium chloride quartz clays. This then gives way outwards to albite clay alteration. The stringer ore is associated with the sericite zone, and the size of the pipe is similar to the Norinda. Cypress type. The semi-conformable alteration is less studied than that of the Norinda type but appears to be similar. Matabi-type. The alteration associated with Matabi-type deposits consists of poorly defined and irregular Christmas tree shape alteration pipe that forms along volcanic faults and then grades upwards into cloud-like zones of alteration which tend to host the VMS deposit. The alteration minerals are dominantly aluminum, silicate quartz, and iron-rich carbonates and/or iron clays, chloride and/or chloratite. This alteration assemblage is similar to those associated with high sulfidation epithermal gold deposits. Volcanism and a massive sulfide deposit felsic system. In the nutshell, you can see here Croco-type and a Matabi-type. In Croco-type, rhyolite or dacite is greater than basalt, less VFD, explosive and passive. Zinc, lead, copper elements you can find. Granodiorite or trondhjemite you can find there. Pre-post caldera composite volcanoes. In Matabi type, rhyolite and dacite are much greater than basalt, much less VFD, dominantly explosive, zinc, copper, lead you can find there. Granodiorite, trondhjemite you can find, and calderas. Cyprus and the Norinda-type, you can see the comparison of the Cyprus and the Norinda-type deposits. Thank you so much for watching.